Okay, welcome back, chemists. We are going to wrap up this unit and look at redox reactions, how we write them, how we balance them. We've done precipitation, we've done acid-base, and now we're just going to look at the last type, what are called redox. Redox reactions, first to just identify them, can fall in a number of different categories. They specifically mean that they involve a transfer of electrons. And we're going to study this later on in the year and how we use redox reactions to actually create electricity because of that electron transfer. For now, we're just going to look at how we write them and how we work with their stoichiometry. Some examples of redox reactions are things like synthesis reactions. For example, sodium can do a synthesis with chlorine to make a much more stable sodium chloride. That would need 2 sodium atoms to make 2 sodium chlorides. A decomposition reaction, which you remember is the opposite of a synthesis. For example, zinc iodide could decompose to make elemental zinc and iodine. That's not a dissociation. We're not making ions. We're making neutral elemental zinc and elemental iodine in this case. And any reaction that has a change in what's called an oxidation state, which happens in the first two as well as almost every combustion reaction. Methane plus oxygen, it'll actually be 2 oxygens, gives us, as we know, CO2 and 2 waters. So that last thing I just said, the change in oxidation number, what does that mean? Well, if we look at redox reactions and there's oxidation numbers, that's how we identify them. Let's define what oxidation numbers are and how we write them out. Oxidation numbers are just a tool that chemists use to bookkeep where the electrons are. We sort of made up this rule that says in a compound, let's pretend the electrons, even though they're shared, let's pretend that they all came from the more electronegative element. And if so, what charges would those things have? It's just a way of tracking electron changes in chemical reactions. And the rules are as follows. Number 1, free elements are 0. So elemental sodium, hydrogen, iron, everything you see on the periodic table would have an oxidation state of 0. Rule 2, there's 6 of these if you're planning ahead. Monoatomic ions just equal the charge. So sodium ion would be +1, calcium ion would be +2, fluoride ion would be -1. Speaking of fluorine, fluorine is -1 in all compounds. And that's because since the rules for oxidation numbers are based on electronegativity, we give fluorine priority and say he's always -1. Unless he's by himself. Obviously, fluorine as elemental fluorine F2 would be 0, but something like sodium fluoride, fluorine would be -1, and obviously sodium +1. Then it gets a little bit more involved. Number 4, the second most electronegative element, oxygen, is -2. In not all compounds, but I'll say in compounds, and put a little qualifier there, that peroxides, O is -1. That's the most common exception you will see to that rule. A peroxide is like H2O2. Rule 5, H is +1, except with metals. And I said there's 6 rules. There are. Those are the main 5. I'm going to put 6 outside the box because it's actually the most important but kind of implied. The sum, that's capital sigma, the sum of all the oxidation numbers will equal the total charge, meaning the total charge that a formula has. So let's practice this. Let's identify what the oxidation numbers are for these 12 compounds that we have over here. Starting with HF, well, fluorine is -1, and H would be plus 1. And there's the sum adding up to 0. There's a net charge of 0 in HF. Water, oxygen is minus 2. There's 2 H's, they'll be plus 1 each. Plus 1 times 2 plus minus 2 times 1 is equal to 0. In carbon dioxide, I don't have a rule for carbon, so I'll start with oxygen. Oxygen is minus 2. The sum would be 2 of those is minus 4, so all the carbons have to add up to plus 4. And then elemental oxygen by itself, that's 0. That's how that works. So why don't you hit pause for a second and go and see if you can identify the oxidation number of every element in the remaining 8 compounds and see how you did. All right, let's check. Sulfur hexafluoride, fluorine is minus 1. There's 6 of them, so the sulfur must be plus 6. The nitrate anion, oxygen is minus 2. 3 of them gives me a tally of minus 6. I'll keep it down below. The sum has to be negative 1. So the nitrogens have to add up to plus 5, which means the one nitrogen is plus 5. Sometimes I like to keep track of what I just call my tally down below it, in case it's a little bit more involved. Mercury is by itself, that's elemental mercury, so that's just 0. HCl is 2 monoatomic ions. Chlorine is minus 1, and H is plus 1. And then we get up to phosphorus trifluoride. Fluorine would be minus 1, so the phosphorus is plus 3. C2H4O2, wow, well let's start with the most electronegative. Oxygen is minus 2. Hydrogen would be plus 1, and then as a result I figure out the carbons. I'm going to keep track of my tally again. 2 oxygens is minus 4. 4 hydrogens is plus 4. That actually means that the carbons have to add up to 0, so each carbon is 0. It has an oxidation state of 0. Then it gets even wackier with Fe3O4. The oxygen is minus 2. That's a total of minus 8 if I keep track. That must mean the irons add up to plus 8. So if you guessed that it's a fraction, you are correct. It is positive 8/3. And you should be going, what the heck does that even mean? How is that possible? Well, think for a second about what this compound might be. You have some iron ions, and there's actually multiple possibilities. There's not just the iron 3, but also iron 2. And they're paired up with some amount of oxygen anions. Oh, not drawn to scale. But there's a crystal of a bunch of oxides and iron ions. And what this actually is a weighted average. There is a weighted average here, and that's why you get a fraction. So we have some iron 2s and some iron 3s, so the net weighted average is positive 8/3. That's kind of rare, but it does happen. Okay, to finish up, the last one was not strange. It was plus 1 for the hydrogens and minus 3 for the nitrogens. Now that we've done that, all that's left is to learn how we balance redox reactions. So let's start with the rules for balancing redox reactions, and then we'll do some practice. They're a little bit more involved than just balancing by inspection like we did in Unit 3. There's essentially 3 rules for how we do this. Number 1, we assign oxidation states. Left to right, you just take every single element, just like we did, and give everything an oxidation state. Number 2, we balance half reactions. And rule 2 is actually a bit involved. It is 3 steps. 1, 2, 3. Step 1, you balance the element that changes. Balance element that changes. Rule 2, balance oxidation number changes with electrons. And that sounds a little strange. I'll show you what I mean. It'll make more sense when we actually do it. And then you normalize to cancel electrons. You'll never have net electrons in the reaction. And lastly, balance charge with H plus or OH minus, depends on if we're in acid or if we're in base, then rest with water. So we're going to assign oxidation states. We're going to balance the element that changes, balance the oxidation changes with electrons, and then H plus and OH minus and the rest with water. So let's do that right now. So let's take a look at this skeletal redox reaction, and left to right, let's assign our oxidation states. First, in permanganate, oxygen is -2. There are 4 of them, so I'm thinking about -8. The total is -1, so the manganese must be, as a result, a +7. The rest are easy, they're monoatomic ions. A 2+ charge is a +2 oxidation state. A 3+ charge is a +3 oxidation state. And a 2+ charge is a +2 oxidation state. No one's going to care if you get that terminology backwards, but for what it's worth, you can teach others that when you put the number followed by the sign, that's a charge. When you put the sign followed by the number, that's an oxidation state. It's okay to get those backwards, but they actually do mean something slightly different. Okay, so let's look at the half reactions. What we have is Fe2+ becomes Fe3+, and then separately permanganate becomes manganese 2. So the first thing I'm going to do is balance the element that changes. So balance the irons. Done. 1 becomes 1. Then I'm going to balance the oxidation state changes with electrons. So each iron goes from 2+ to 3+. Each one gets oxidized and loses an electron. And then I'll balance the charge, although it's already taken care of. 2+ on the reactants, 3+ and 1- is 2+ on the products. And I don't need to balance any H pluses or OH minuses. This is done. This is a correctly balanced half reaction. Let's do the manganese. Manganese is already balanced. The oxidation state, well, each manganese goes from +7 to +2. So each one gets reduced, and as a result, it gains 5 electrons. And actually, that's where I'm going to stop, because once you have that, doing hydrogen ions and hydroxide ions, we're going to just do that at the end. It's easier to squeeze that in at the end and do it for the whole reaction. All you really need are these electron counts, because now I know I need to multiply this first one by 5. And then I'll balance the rest by inspection. So I'm going to have 5 Fe2+ plus 1 permanganate will make 5 Fe3+ and a manganese 2. And now I'm going to balance the charge with ions. We're going to do H+, we're going to say in acid, and then I'm going to balance the rest with water. So what's my charge? Well, I have 10+ over here and 1- over there. So it looks like I have a total of 9+ over here, or really +9 is my net charge on the left. On the right, we've got 5 times 3+ and 2 more. That's 17+. So we were +9 here and +17 over here. So we are missing a difference of 8. I need to make the left 8 more positive or the right 8 more negative. We're in acid, so I can add H+. So I'm going to make the left side more positive by adding 8 H pluses. Now I'm going to balance the rest with oxygen, with water molecules to balance the oxygens. And the only place I see them are in the permanganate. So there's 1 oxygen for every water. So I would need 4 water molecules. And look what happened. As soon as I did that, I automatically added 8 extra H's, and it takes care of what I just did. So you'll know you're right if that works out in the end, like so. There's your completely balanced redox reaction. You can always tell 5 irons goes to 5 irons if you just check 1 manganese, 1 manganese, 8 H's, 8 H's, 4 oxygens, 4 oxygens. Check the charge. We've got 10 plus and 8 plus and 1 minus. That's positive 17 on the left. 5 times 3 and 2 more positive, positive 17 on the right. This is balanced. So let's practice a few more. We're only going to do acid, but let's try to do the same thing. And I'm going to try to take as many shortcuts as I can along the way, and hopefully you'll be able to do a few on your own after this is done. So let's start with oxidation states. I don't have a rule for chromium. Oxygen is -2. That gives me a -14. Has to be 2 negative total, so the chromiums are +12, which means each chromium is +6. Fe2 plus, +2. Cr3 plus, +3. Fe3 plus, +3. Now, let's write some skeletal half reactions. So we have Cr2O7 2 negative becomes Cr3 plus. We also have Fe2 plus turns into Fe3 plus. Now I'm going to balance the element that changes. 2 chromiums has to become 2 chromiums. The second one's already done. 1 iron becomes 1 iron. Now I'm going to balance the oxidation state change by adding electrons. So each chromium goes from 6 to 3. So each chromium gains 3 electrons, but I have 2 of them becoming 2 of them. So this is actually a 6 electron reduction. Let me say that again. Each chromium went from +6 to +3, so each one gained 3. That means 2 of them gain 6. The iron is easier. The iron loses 1. And now I normalize. I keep this one the same, and I multiply the iron one by 6. And now let me put that back up in our skeletal up above. That means my dichromate has a coefficient of 1, my iron 2 has a coefficient of 6, my chromium 3 has a coefficient of 2, and my iron 3 has a coefficient of 6. But we're still not done. However, that's the most important part. That electron count was all I needed to figure out the coefficients of the main things that are involved in the redox. We still have H pluses and likely water molecules. So it's actually personal preference which one you do first. I like to do the H pluses first because it takes care of the charge, but I'll show you that you can actually do water first instead. In fact, some people think that's easier because you just look for the oxygens, and that's what water takes care of. So I have 7 oxygens on the left. That must mean I'm going to need 7 waters on the right, because it's the only thing that brings water in. And now I take care of the rest with hydrogen ions, H+. We have 7 times 2, that's 14 H pluses. So I'm going to need 14 H pluses on the left. And there's our balanced reaction. We are done. You can check. 14 H's, 14 H's. 2 chromiums, 2 chromiums. 7 oxygens, 7 oxygens. 6 irons, 6 irons. Let's check the total charge of the reactants. This is 14 positive and 12 positive more. That's already 26, and then 2 negative makes this plus 24 on the reactant side. The products, we have 6 positive and 18 more. That is also 24 positive. So they're both 24 on each side. The total charge in the reactants is the total charge of the products. So now that you've done that, try the next 2. Assign oxidation states, balance the skeletal half reactions, and then balance the whole thing. Okay, let's check those oxidation states first. This is a peroxide, so oxygen is -1, H is +1. Nickel 2, +2. Nickel 3, +3. Water, +1 for the hydrogen, -2 for the oxygen. Let's write out some skeletals. Peroxide, it becomes water. Nickel 2 becomes nickel 3. First up, balance the element that changes. In this case, it's the oxygens that change. So I actually need to put a 2 in front of the water on the product side. Now I'll balance using electrons to take care of the oxidation state. That changes. So each one goes from -1 to 0. So each one loses 1 electron, but I have 2 of them, so they will lose 2. So I'm going to put plus 2 electrons on the product side. Then the nickel, that's a little bit easier. Each one goes from 2 plus to 3 plus, so then that means it loses 1 electron. Oh, something is up here. Ah, I know. I made a mistake, didn't I? That's okay. Oxygen goes from -1 to -2. Hopefully you caught that. You're probably going, what's he talking about? He's totally wrong. Yep, that's okay. Everybody makes mistakes. Just go back and fix them. So we go from -1 to -2. Each one gains 1, 2 gain 2. Okay, so I need to double the nickels and keep the waters in that skeletal the same. So the peroxide will have a coefficient of 1, the nickel 2, 2, the nickel 3, 2, and the water 2. Now let's take care of waters or hydrogen ions. Waters are already in this, so I'm actually going to look at hydrogen ions for this one and see if that needs to change. Let's check the charge on the left. We have 2 times 2 plus. This is positive 4 on the reactant side. And then here we have 2 times 3 plus. That's positive 6 on the product side. So I need to make the reactants more positive. So that means we need 2 more H plus ions. And then that should take care of the charge. And then you balance the rest with waters. But if you look, you're actually already taken care of with those water molecules. That fixes everything. And if you go back and check, it's done. We didn't actually have to add any additional water molecules to this reaction. We just needed hydrogen ions. Okay, last one. First, oxidation states. I'm going to try to make this one even more abbreviated, and I'll show you how. Oxygen is -2, therefore chlorine is +1. In this chromium ion, oxygen is -2, so the chromium is +3. Chloride is -1. And then chromate, oxygen is -2, so chromium is +6. Now, I'm not even going to write out the half reactions. I am just going to sketch the electron change that kind of goes with each. Each chloride changes by 2 electrons, and each chromium changes by 3 electrons. So I didn't write out the half reaction, but I know that if I did, I would have these chlorine-containing compounds, and there'd be 2 electrons in it. Because remember, the 2 electrons takes care of this +1 becoming -1. Frankly, it doesn't even matter for the purposes of this to know which side of it's on, if it's on the reactants or the product side. I know it's going to have a 2 in front of it, or a 2 electron in it. Likewise, 1 chromium of +3 becomes 1 chromium of +6. It changes by 3. So now I can picture in my head these half reactions with a 2 electron in one and a 3 electron in the other. That must mean I'm going to have to triple the chlorines and double the chromiums. And there, that becomes my coefficients. So I put 3s in front of everything with chlorines and 2s in front of everything with chromiums. And now I balance the rest by inspection. I'll do oxygens first. So we have, it looks like 3 plus 4. We have 7 oxygens, but 8 over here. So I need 1 more oxygen, and it'll come from a water on the left-hand side. And what's left is hydrogen ions. Looks like I have 2 hydrogens on the left and none on the right. So I'm going to need 2 hydrogen ions on the right. And that should take care of it. So let's check. Every element should be balanced, and every charge should be balanced. 2 H's, 2 H's. 1 oxygen plus 3 and 4 more gives me 8. 2 times 4 gives me 8 oxygens. 3 chlorines, 3 chlorines. Already did oxygen. 2 chromiums, 2 chromiums. Elements are balanced. Let's check charge. On the left, we have 3 minus. 2 minus more makes 5 minus. So this is -5 on the reactant side. And the products are 3 negative, 4 negative, that's 7 negative, and 2 more positive. It's -5 on both sides. So the charge is balanced. the elements are balanced. All of these are now balanced reactions in acid. So as you can tell, it's a bit more involved when you're balancing redox reactions, especially when you have to add these extra water molecules and hydrogen ions. If we were in base instead of acid, the only thing that's different is you add OH minus to balance the charge. That's a little bit trickier just because OH minus also brings in oxygens. So I often do that first before adding any water molecules, but it's always wise to check in the end. And that's how you balance redox reactions.